Alright, this is 2011, number 5. We'll roll through this guy. Here we go. It says hydrazine, an inorganic compound, N2H4. It says in the box below, complete the Lewis electron dot diagram for N2H4, drawing all the electron pairs. So here we go. Each nitrogen has 5 valence electrons apiece. That's 10 electrons, 11, 12, 13, 14 electrons, 7 pairs. Get your 1 between every one of them first. That gives us 5 pairs. And so the other 2, you can't do double bonds in between them. They'll violate the, or triple bond in between, you'll violate the octet rule. Nitrogen can only have 8, and so there are the other 2 electrons. That gives the nitrogens all 8 valence electrons, hydrogens all 1 apiece, and there are your 7 pairs of electrons. That's what she looks like. Then it says in part B, on the basis of the diagram you can be in A, do all 6 atoms in the N2H4 molecule lie in the same plane? Explain. So they're asking, is this a planar structure? If we look at either one of the nitrogens, this has 3 domains. This nitrogen here has 3 things connected and 1 lone pair. That's 4 domains. And so I would talk about each nitrogen in part B takes on what geometry? Each nitrogen in N2H4 has a pyramidal shape. You can say trigonal pyramidal shape, that's fine. Has a pyramidal shape. So the structure cannot all lie in the same plane. That's the answer on part B. Those nitrogens there are all trigonal pyramidal shape. So it gives us that kind of tetrahedral base structure, that 4-domain structure. Part C. The normal boiling point of N2H4 is 114. The normal boiling point of C2H6 is -89. Explain the terms. Explain it in terms of intermolecular forces present in each liquid. Why is the boiling point higher? Hydrogen bonding occurs between hydrogen, oxygen, nitrogen, and fluorine of corresponding molecules. So this guy has hydrogen bonding, and so it talks about intermolecular forces present in each. So I would put it this way: N2H4 has dispersion forces, dipole forces, and hydrogen bonding. Where C2H6 only has dispersion and dipole forces. And looking back at that, I could probably shorten that up by saying they both have dispersion forces and dipole forces, but N2H4 has additional hydrogen bonding. The hydrogen bonds or the hydrogen bonding is stronger and increases boiling point. And if you've stuck with me over the last 4 or 5 weeks and done all these FRQs, you've written that 15 times now. It should be something you're really comfortable with. So this is the key to victory, right? So you do need to talk about all their intermolecular forces, and then the hydrogen bonding is a stronger intermolecular force and increases boiling point for the N2H4. Good. Part D. Part D says write a balanced chemical equation for the reaction between N2H4 and water. That explains why a solution of hydrogen in water has a pH greater than 7. Here's the key to victory. If I just am given N2H4 and water and it says write the equation, I too am confused about what they want. The good part for us is it says the pH is going to be greater than 7, which means that this solution has to be basic, right, on the product side. And so here's how I start. I know my reactants are N2H4 and water. And they told me my product, in order for the pH to be bigger than 7, if you're not sure, then your first product is a basic particle. And so that's what I did. And when I look at this, now I can figure this thing out. Which one of these turned into hydroxide? That one did. How did it turn into hydroxide? It donated a hydrogen away. And so when that donated hydrogen, it turned into hydroxide. N2H4 became my hydrogen acceptor. And so it becomes N2H5, and it gained that positive charge. That's my equation. That's what it looks like. It says write the balance equation. The fun part about it is it's already balanced. It's only one point there. It's really that second piece of information there that gives us what we need in order to write that equation. So that's one of those where you have to figure that out. You have to trust your training a little bit and go, okay, how is the pH going to be greater than 7? I've got to have a base. How can I make these things basic? Get your base on that side, and then work from there. And so that's part D. It's a little tough, just because you haven't seen it. Then part E says N2H4 reacts in the air according to the equation. Gives us that it's exothermic. Delta H is a big negative value. Is the reaction an oxidation, reduction, acid base, or decomposition reaction? Pure elements scream at you oxidation, reduction reaction, because that means the oxidation number on both of those is going to be 0. And so if those are zeros, then we can look at what their other oxidation numbers will be. I know that hydrogen is a +1 here and oxygen's a -2 in water. I've seen that one all the time. If oxygen's going to change and nitrogen's going to change, that means hydrogen has to stay the same. So that hydrogen has to be a +1 on N2H4, which makes that N2 a -2. And so it's an oxidation reduction. Because oxygen goes from 0 to -2. You can even put reduced. Nitrogen goes from -2 to 0, oxidized. Justify it with the oxidation numbers, write them in there so that they know you know what you're talking about, not just guessing, right? It's oxidation reduction, that's why it's oxidation reduction, because of those oxidation number changes. You can only have one reduction and one oxidation. Part F says predict the sign of the entropy, change the delta S for the reaction, justify your prediction. Here we go from what? 1 mole of gas to 3 moles of gas. And so our delta S should be positive. We're increasing the randomness or disorder. So answer the question first. Positive delta S, and then justify that thing, because we have an increase from 1 mole of gas on the reactant side to 3 moles of gas on the product side. More disorder is a positive delta S. That's F. That should be a point for us. It should be a good point for us. And then part G, last piece of this one, indicate whether the statement in the box below is true or false. Justify your answer. Here we go. A large negative delta H for the combustion results from the large release of energy that occurs when strong bonds of the reactants are broken. Alright, so if the bonds are broken, did we have to put energy in or did we take energy out? Was energy released? Breaking bonds, you have to add energy. And so on that's the big one for me, the reason that this is false. False. Breaking bonds takes energy. It doesn't release energy. That's the first part. You can also come back and justify it, and that's fine. If you do that, you're in great shape. The second part of that is if it took a bunch of energy to, large release of energy that occurs when strong bonds of reactants are broken. If you released a bunch of energy when the bonds were broken, then the bonds formed would have to be huge in order to do this negative 534. And so they've got it backwards there. So the bonds and the reactants, in order for this to be negative 534, the bonds and the reactants have to be way weaker than the bonds and the products. And that's not the case here. It wouldn't work that way. The bonds of the reactants have to be weaker than the bonds in the products. That's where that negative comes from. I think this is the easy falsification here. Breaking bonds takes energy. It doesn't release energy. Good? And you're all set for 2011, number 5.